Hello, everyone. I'm Zeke Wang. Now I'm a tenure-track assistant professor and also a research professor at Zhejiang University. Today is my pleasure to talk about my work in MLWeaving. So this world is moving in three directions. So the first one, okay, there's a delay here. So, sorry. Oh, sorry. The first direction is big data. So our data is getting larger and more complicated. So we need data processing system to help us to manipulate our data. For example, like database systems, Spark, Hadoop, or TensorFlow. The second direction is machine learning. There's a lot of machine learning models, like a linear model, neural network, and decision tree, and so on. So the third direction is the new hardware, because our data is getting bigger and our model are getting larger. So it means that we need a lot of computer power to process our data, such that we can get the useful information out of the data. But the general purpose computer units cannot provide such a computing power. So we resort to heterogeneous hardware or new hardware to get more computing power. For example, like NVIDIA's GPU, Google's TPU, or Intel's FPGA. So about FPGA, I want to say a bit more. Now the cloud provider like Alibaba or Microsoft provides servers featuring FPGA to provide this real-time service. So this work is just intersection of these three directions: database, linear model, and the FPGA. So the goal of this talk is answer the following question: can we use the FPGA to accelerate linear model training? Of course, our answer is yes. We can achieve 11 times speed up compared to the fastest CPU implementation we know. To achieve this speed up, we use software hardware co-design approach. So from the machine learning perspective, we use low precision training. From the database perspective, we use the new data structure. And from the hardware perspective, we have efficient hardware design. Combine these three directions together, we can achieve 11 times speed up. So here's the outline of my work. So first, I will give the quick background. So what is a stochastic gradient descent, SGD? SGD can allows synchronized execution or asynchronous execution. And SGD also allows low precision. Then I will talk about my design, MLWeaving. MLWeaving enable any precision training and also efficient synchronous design. First, I will talk about the background. So, okay, how does the SGD work? So, SGD has three components. First one is training data. Second one is computer device. Third one is a model. So, SGD first will read the data, then read the model. The third step is computer gradient. The fourth step is to accumulate the gradient to the model. Then go back again. The first step is to read the data, read the model, computer gradient, and accumulate the gradient to the model. So SGD have two interesting features. First one is the model can be scaled, especially when we run the SGD on multiple cores. Second one, SGD can be done in low precision. So the training dataset can be low precision and the gradient can be low precision. So for our MLWeaving paper, we just only focus on the training data can be low precision. So why we care about the low precision? So I will give the the intuition behind the low precision. So suppose we have a really simple machine learning task to tell the pictures it contains a cat or not. We assume that the output of this machine learning task is ranging from 0 to 1. Suppose the output is bigger than 0.5, we can say that the figure contains a cat, otherwise not. So we assume that the model contains only a simple multiplication. If we do the multiplication in full precision, like the left side, 1.3102 times 0.6020, the output is 0.7888. So we can see that the result is larger than 0.5. We can say that the picture contains a cat, but we can also do it in low position, like the right side. We can say the computation like at 1.3 times 0.6. The result is 0.78. Even though the result is a bit different from the full precision part side, but still low precision still can do the job because 0.78 is still larger than 0.5. So, so for the machine learning perspective, it still works because machine learning is can tolerate the computation errors. But we also observe that so different machine learning might need different precision levels. For example, like for this figure, maybe for this model, we only need a 3-bit. For this model, maybe we need a 9-bit. So it's different. However, for the hardware, now our hardware cannot support low precision very well. For example, like for the CPU, can only support 8-bit, 16-bit. For the GPU, it can only support 8-bit or 16-bit. And for the TPU, can only support 8-bit. But the thing is that, so because for different machine learning tasks, we may want to, probably it needs 4 bits. So what we need to do on modern hardware is to pad the data to the 8 bits and then to do the further computation. Then we know that it's not our new hardware cannot support the low precision very well. So the question here is that maybe can we do something enable things that cannot be well done on CPU? So our answer is yes. We want to support any precision training plus high throughput synchronized design. Now I will talk about the MLWeaving. Before I go into the details, I really want to emphasize the 2 goals of our any precision training. Basically, I use the first principle thinking to deduce the 2 goals. The first one is we want to use 1 hardware design and 1 copy of dataset to support any precision training. Second one is our design needed to achieve linear speed up with lower precision. If we achieve these 2 goals, we can say that our hardware design or our system is close to optimal. So in order to achieve any precision training, we need this hardware software co-design. From the hardware side, from the software side, we have our MLWeaving memory layout. So why we need the MLWeaving memory layout? Because we have 3 observations. The first one, the memory bandwidth is always the performance bottleneck. The second one, the low precision can provide reasonable, good training quality. Always 8-bit is always enough. The third observation is that even for the same data set, different training tasks might need different precision levels. So the question here is that, can we store the data in a new data structure that efficiently support arbitrary position data movement? Our answer is yes. It's our MLWeaving memory layout. Before I talk about my memory layout, I want to say a bit about how the modern system store the data. So it's store data in row-wise. First store the first row, and then we store the first feature, and then we store the first bit of the first feature, second bit of the first feature, third bit of the first feature, and the fourth bit. We assume that each feature has 4 bits. Then we go to the second bit, first bit, second bit, third bit, and fourth bit. And we also assume that each row have only 2 features. Then we go to the second row, the first feature and the second feature. Then we talk about how MLWeaving store the data. It's also row-wise, but here's the difference. So we store the first bit of all features of the first row together, like this. The blue bits are stored together. Then it go to the second bit, and third bit, and fourth bit. After we store the first row, we go to the second row. First bit, second bit, third bit, and fourth bit. So it may be more complicated when a row have thousands of features, but the basic idea is similar. So advantage of such a memory layout is that if we want to just one bit, then we only need to read the blue bits. And if we need 3 bits position, then we don't need to read the fourth bit. Such a memory layout looks appealing, but on modern CPU or GPU, MLWeaving memory layout doesn't work well because CPU or GPU doesn't have custom instruction for this memory layout, and then we have to group bits using normal instructions from different memory locations before the further computation. So the cost is really high. Actually, we have did a few experiments about this. Suppose we group 8 bits together and do the further computation, then the performance will be lower than we directly computing on the 32 bits floating point. Then we need a hardware design to support our new memory layout. The key idea of MLWeaving hardware design is that we use bit serial multiplier to enable efficient data processing from the MLWeaving memory layout. So how the bit serial multiplier works? So I will give a concrete example to show how bit serial multiplier works. Before I talk about the bit serial multiplier, I will say a bit about the normal multiplier. Suppose our data is 4 bit, full position is 4 bit, and then so each bit should be binary. But in this example, I will use decimal numbers for easier understanding. Suppose we did it in 3 bits, so just one operator. One number is low position. Then for the low position, we also do on the begin with the least significant bit, and for the 2 bits like this, and 1 bit like this. So now I will talk about how the bit serial multiplier works. Bit serial multiplier has 2 components. The first one is bit serial part. Second one is a bit parallel part. So suppose we accumulate bit by bit into our result. Suppose we do the 1 bit position, then we read the most significant bit from memory and feed into the bit serial multiplier, like this. The 4 means 4,000. So the sum becomes 80000. So Suppose we only need the 1 bit position, then the result is the same as the left side. But if we need a 2 bit position, so we keep reading the bit 3 from the memory and feed into the serial multiplier. The 3 means 300. So the result will become 86000. If we only need 2 bit position, so we can just proceed to the next computation. But if we want to do the 3 bit position, so we can keep reading the 3rd bit 2 from the memory, and as 2 means 20, and the result becomes this. So also, if we want to do the 4 bit position, then we read the least significant bit from the memory and feed it into the bit serial multiplier, and then the result becomes this. Okay, so I don't want to go too into the details of our hardware design. I just want to show where we use the bit serial multiplier. There's 2 places we use the bit serial multiplier. First one is we do the dot product is here. Actually, we have 512 bit serial multiplier here. And the second one is when we use bit serial multiplier is when we compute the gradient is here. And here is we still have 512 bit serial multiplier. So we can say that we compare the bit serial multiplier and the MLWeaving memory out to enable any precision machine learning training. So here now I will talk about our MLWeaving performance. We can achieve almost linear speed up with lower precision with just only 1 hardware and 1 dataset copy. The x-axis is the precision level, y-axis is speed up over 32 bits. So we can, the blue bars shows the ideal case, and the black bars shows our MLWeaving speed up. So we can say that we can achieve almost linear speed up, except for the case when the precision is one bit, because the pipeline overhead is a bit higher, then we cannot achieve linear speed up for a 1 bit case. But we always don't want to use 1 bit dataset to training because we lose a lot of information here. We at least use 2 bits. We also care about the memory traffic because the memory consumes the majority of the overall system's power. So, but we can see that our MLWeaving design can reduce the memory traffic linearly when we reduce the position. Now I will talk about our efficient synchronized design. So, so SG on the CPU is synchronized or asynchronous. Actually, we can do it in both ways. First, is our synchronized. First is synchronized. Synchronized happens on a single core SGD. So its throughput is really low, and because it has like read after write dependence regarding the model X, so it will have trouble when we want to apply SGD on multiple cores. So when we really want to run multi-core SGD on the multiple core, so we need to rely on the asynchrony. There's 2 state-of-art asynchronized SGD design on the multiple CPU. First one is hardware. Second one is the model average. I will talk about a bit how the hardware and the model average work. So for the hardware, suppose we have 2 cores and one they share the same copy of the model. Then hardware will, for each core will read the model and update the gradient to the model regardless of the other core. So so it's asynchronous design, but the hardware can still converge when the dataset is sparse. But its throughput is not that high because there's still a cache coherence overhead on multiple CPU, especially for the dense data. The issue here is that when the one core wants to read data to the cache, then the first thing the core need to do is to invalidate the other copies in the other cores. Since the invalidation overhead is really high among the CPU. The second approach is the model average. What the model average do is that each core has its own copy of model. Then each core can work on his own local copy. Then at the end of each epoch, the local copy will be averaged. Then we can have the global model. But the problem here is that the model average can converge really slowly because when we compute the gradient, so it will always read the local model, not the global model. So to sum up, so on the CPU, we may achieve either high hardware efficiency or high statistical efficiency. But suppose now the question here is, suppose we have custom hardware. We want to synchronize HDD or asynchronous HDD. So our goal is to achieve best of two worlds. So we want to higher hardware efficiency and high statistical efficiency. Before I go to our final design, so I will first talk about the original synchronized design. It can be computer bound. The key idea is to keep the read after write dependency regarding the model X. Now I will show you how it works. So for the first batch, it will read the model and compute the gradient, and then after that we will accumulate the gradient to the model. After that, we will read the second batch and compute the gradient, and then accumulate the gradient to the model. We can see that the hardware utilization is around 50%, so it can be computer bound. But we observe that the custom hardware can update the model at the fine gradient. In our case, it's like we can do it like in terms of 64 weights, not the whole model. So we follow the one technique from computer architecture. It's called chaining. So what we do is here. So when we accumulate the gradient from the first batch to the model, so we don't need to wait so all the gradient accumulated to the model, but we can do that like after we accumulate part of the gradient to the model, we can inform the second batch to read the updated model. Then something like this. So then we can we can do the model update and the computation at the same time. Then the gap is really small here. Now, then our synchronized design can be as fast as asynchronous design. Then our approach becomes memory bound. Now here I will show how is the effect of the synchronized design. So because the CPU implementation like Hogwarts and model allergy is asynchronous design, so our MLWeaving is synchronized design. So we MLWeaving need much less number of epochs to converge. Here's I will talk about bit about our takeaway message here. So when we want to design a hardware for specific algorithm or application. So we better to do something like to the things that can be well done on the CPU or GPU. Then our hardware design will pay off. It means that we cannot do another design. We can enable a new design. To sum up, we want to do an end-to-end performance comparison. So we also compare with the hardware and the model edge. The model hardware and the model edge run on an Intel CPU. It has 14 cores. We use the AVX2 and also with the low precision. Our MLWeaving is we use 3-bit precision. Actually, we can see that MLWeaving is like is an order of magnitude faster than the model edge. I really want to say here, so because our FPGA is not that big one, it's not state of art, and its memory bandwidth is like a fourth of the CPU, but we can still achieve significant performance speed up because our any precision design and our synchronous design on the FPGA. We also compare the memory traffic consumption, memory traffic. So we can see that when we the machine learning task converge, MLWeaving needs really much less memory traffic. It means that our MLWeaving can provide a really significantly energy efficiency than we run on the CPU. That's all. Thanks. Any questions?